Okay, in this video I'm going to give some examples of applying the rules for the various types of digital encoding schemes. And basically the idea here is that we've got our transmitter here, and this is an important part of what the transmitter does, is it takes its data as input and creates a signal or a waveform as output. The signal is typically some voltages going up and down. And these encoding schemes apply widely to Ethernet, to things like FireWire or USB signals, and so they're all over the place. And I hope that these, it's really an exercise in applying the logic of these rules. And so I hope these problems are sort of fun in that regard. And I've got one example of each of the 8. And I've started here with the NRZ, which is the easiest of them all. And I've already filled this one in. 0 gives a 0 volt, 1 gives a plus V. And let's see if I have the thick pen I was looking for. Yeah, we do. Okay, so I got a 0, 3 1s in a row, a 0. So the voltage goes up and down with the 0s and 1s in about the simplest way you can come up with. So this one's pretty easy. NRZ stands for non-return to 0, and that'll be in contrast to the return to 0 coming up. That goes back to 0 in the middle of each bit period. So what we're looking at here, just to be sure, is the time axis, the voltage axis on the vertical, and this is showing, and each of these squares is 1 bit period. And so you can see the bits here coming, each bit has its own bit period. Let's look at NRZL. Here we have the pattern is, during the bit period, the pattern is a constant voltage, either plus or minus V naught, and a 0 gives a positive voltage and a 1 gives a negative. So this is, again, about as easy of a pattern. It's seems kind of backwards. A 0 gives a positive voltage and a 1 gives a negative voltage. So I got 3 1s in a row, a 0, a 1, 2 zeros, another 1, 0, 1, 3 zeros, a 1, and a 0. So this is almost as simple as NRZ, and this is NRZL. Okay. Let's see here. NRZI, the I stands for inverted. The rule is that during the bit patterns we have a constant voltage, either plus or minus V naught. And NRZI is kind of tricky because here we have, for a 0, no transition at the start of the bit period, and a 1 we have a transition. Okay, and so the trick to doing this one is to draw the transitions first, basically. And here we have to assume that we have to know what the previous voltage was. So for example, here on the 0 I have no transition, but no transition from what? Was it plus or minus V in the previous bit period over here that we don't have? And I'm going to assume it was plus V as a starting point. And so a 0 means no transition at the beginning of the bit period. A 1 means we transition at the start of the bit period. And once we transition to a voltage, we stick on that voltage, constant voltage during the bit period. Now a 1 means we transition at the start of the bit period. 1, transition again. 0, don't. 1, transition. 0, don't. 0, don't. 1, transition. 0, don't transition. 1, transition. 0, don't. 0, don't. 0, don't. 1, transition. And 0, don't. So there's the waveform that results from the NRZI rule. Okay, and you can see that to the left of every 1 is one of these vertical lines, and to the left of every 0 is not a vertical line. Okay, so that's the NRZI. RZ stands for return to 0, and let's see, the rule is that we have the pattern during the bit period is the pattern as shown here. And what that means is that we have either, and so in brackets is shown the voltage in the first half of the bit period and then the voltage in the second half. So every single bit period we return to the 0 voltage in the middle of the bit period. Again, first half, second half. And a 0 gives a minus V0 to a 0, and a 1 gives a plus V0 to a 0. So this is RZ. And what I'm going to do, the easiest way I think, is to do all the zeros first. They're a minus V0 to 0. And if I fill in all the zeros first, you can see how this works. You see I have to connect these things after I've made the transitions. Now the ones go from plus down to 0, like this. Okay. I'm going to do all the ones now, and then I'm just going to connect up the voltages. Okay. After I do all the zeros and ones, I do have to have a voltage pattern here, so I can connect these guys up. And this is my signal then. Okay. This is the waveform that's produced from that bit pattern. Okay. Hope that's clear. Next, Manchester. In Manchester, we have the pattern as shown. There's a transition in the middle of every bit period, just like the previous one. And a 0 goes from positive voltage down to negative, and a 1 goes from negative to positive. And this is another one where I'm going to do all the zeros first, positive down to negative, like this. 0 is plus V0 to minus V0, right. Plus to minus, plus to minus. And you see I have to connect these guys up after I'm done creating the pattern for each bit. 0 goes from plus to minus. 1 goes from minus to plus, like this. They don't all connect yet, but I'll do that at the end, from minus to plus. Some of them do connect as I make them, like this one, like this one. This one connects minus to plus on the ones. The ones that aren't connected yet, I just come in at the end and I fill them in. Kind of neat. Okay, so there's Manchester. Let me move through these things here. Differential Manchester. Oh boy, this one looks complicated. The pattern is that we have a transition in the middle of every bit period. And here's the two patterns, kind of like Manchester, except what you do is you fill the pattern in based on the value of the voltage at the beginning. So if the voltage was a plus V0 at the beginning, then you fill in the pattern that starts with the positive voltage. If it was negative, you start with the one with the negative. And here's what we have. 0 gives a transition at the start of the bit period. 1 gives no transition. And this requires the knowledge of the previous voltage level to get us started. And I'm going to assume that the previous voltage level, so 0 is a transition at the start of the bit period. I'm going to assume that the previous voltage level was a plus. And so the 0 gives me a transition at the beginning, from plus down to minus. No matter where it is, the 0 gives me a transition at the beginning of each bit period. So I'm filling in the transitions on the zeros. So when I have a 0 bit coming in, I have a transition at the beginning of its bit pattern. And I'm filling those in. 0, 0, 0, 0, and 0. The ones, however, don't. And what I'm going to do then is I'm going to now go ahead and enter in my patterns. If it's negative at the start, I go like this. And the 1 does not give me a transition, so I continue straight on. I guess I'll ignore that. 1 doesn't give me a transition, so I continue straight on. 1 doesn't give me a transition again. And so you can see here that the 1s, I have no transition at the beginning of the bit period. And I'm going to go ahead and continue with this. 1s give me no transition at the beginning of the bit period. And so I always just draw this little shape 1 gives me no transition at the beginning of the bit period. Transition, no transition. So I'm always drawing either plus to minus or minus to plus. A 1 gives me no transition at the beginning. Okay, and that's how you fill in the differential Manchester. This is probably the most complicated of all of them. Okay, let me go ahead and go to the next page. I've got AMI. I've got 2 more to do. I'll do them as quick as I can here. AMI, the pattern consists of either it's a constant voltage, a 0 is a 0, and a 1 gives an alternating between plus and minus. As before, we need to know the previous voltage to get started. Let's suppose it was positive. So a 0 gives me a 0, and a 1 gives me the opposite of the last voltage. And so since the previous one was positive, I'm going to go negative. Now each time I get a 1, I flip it over to the other voltage. Each time I get a 0, I stay on 0. So I get these zeros, and then the 1s just alternate up, down, like that. Okay, that one was fairly straightforward. It alternates between positive and negative. Finally, pseudo ternary. The pattern is constant during the bit period. It's just very much like AMI. The 1s give me the 0 voltage, and the 0s alternate, and again we need the previous voltage to get started. Let's say it was positive. The 1s are giving me the 0s this time, and the 0s alternate, and if the previous one was positive, then I go down, and then I go up, then down, then up, then down. Notice 2 zeros in a row. I go up, then down, then up. Then I go up, then I go down, then up, then down finally. Okay. So this is a summary of all 8 of those line coding examples. Hope this helps.